All right, welcome to the Explainer. Today we are pulling off a literal mathematical heist. We're going to infiltrate the complex plane to try and steal the absolute identity. Our main target for this job, a truly fascinating concept from linear algebra and ring theory known as commutators of finite multiplicative order. We're going to dive right into what actually happens when the fundamental rules of mathematical operations completely clash and how exploiting those clashes can literally unlock profound, hidden structures inside these seemingly abstract spaces. So, let's dive right into what sounds like an absolutely impossible mission. We're looking for two matrices, let's just call them A and B, whose mathematical clash somehow generates the pure, absolute identity matrix. Now, you know that with standard, everyday numbers, the order of multiplication totally doesn't matter, right? 3 times 4 is exactly the same as 4 times 3. But in the wild world of matrices, order is literally everything. A times B almost never equals B times A. And it's precisely this friction, this exact difference, that we are trying to exploit to equal pure identity.
Think of matrices A and B as our primary tools here, and their clash? Formally, that's called the commutator. Mathematically, we write this out in brackets as AB, and we calculate it simply as A times B minus B times A. You can kind of think of the commutator as a highly precise measuring tool. It measures exactly how much the sequential order of your variables matters. If they commute perfectly, the commutator is just 0. But we want something way more ambitious than that. We actually want this clashing force to equal the identity matrix.
But wait, here is our first massive security firewall. If you take the trace of a matrix, which, as a quick refresher, is just the sum of the elements right down its main diagonal, a fundamental law of linear algebra states that the trace of any commutator of complex matrices is always going to be exactly 0. Always. But our target? The identity matrix of size n? It has 1s all the way down its diagonal, which means its trace is always n. So a commutator can literally never equal the identity matrix directly. A direct hit is mathematically impossible. The vault is locked.
Since kicking down the front door won't work because of that trace 0 firewall, we've got to apply a brute force multiplier. We are going to take our commutator and we're going to raise it to a finite power, which we'll call k. By multiplying the commutator by itself k times, we introduce these crazy non-linear combinations. The hope is to basically bend the mathematical rules just enough to slip right past that trace restriction.
Which brings us to the ultimate question. What exactly are the magic numbers for k and n that actually make this seemingly impossible equation a reality? This right here is our breach equation. The commutator of a and b raised to the power of k equals the identity matrix of size n. Finding those exact, perfect combinations of power and size is quite literally the only way to successfully crack this vault.
To actually break this encryption, we've got to rely on this beautifully elegant theorem by mathematicians Lamb and Leung. They proved that our big matrix problem is actually just hiding a complex number problem. To crack it, we need to find n many kth roots of unity that perfectly cancel each other out, adding up to exactly 0. It's like a giant puzzle. The set of all possible matrix sizes n that allow this complete perfect cancellation for a specific power k, that is what we call the weight set of k.
Let's look at the actual passcode. Lamb and Leung's theorem gives us this surprisingly clean arithmetic rule. The heist only works if our matrix size n is a sum of the prime divisors of our brute force power k. That is the master passcode. So if k is, say, a prime number itself, then n simply has to be a multiple of that prime. It is a stunningly simple condition for such an insanely complex algebraic lock.
Okay, let's ground this with a real concrete example so you can see it in action. Say we use a brute force power of 2 to infiltrate a 2 by 2 matrix. So k is 2 and n is 2. We can just use a really simple diagonal matrix with entries 1 and -1. Now, notice its trace is perfectly 0, so it acts just like a valid commutator. But when you square this matrix, well, -1 times -1 becomes +1, and boom, it slips right past the firewall and squares perfectly to the 2 by 2 identity matrix. We're in.
But here's where things get absolutely mind-blowing. Mathematicians Khurana and Lamb took this whole concept even further. They realized that this kind of commutator relation isn't just some neat party trick. It actually acts as a structural master key. They found that if you have just a single commutator relation squared equaling identity inside a mathematical ring, it forcibly dictates the very shape and structure of that entire mathematical universe.
So naturally, we've got to ask ourselves,
Could we pull off this exact same mathematical heist inside the totally abstract, highly secure architecture of an arbitrary mathematical ring? Think about it. We're leaving the comfortable, well-known world of complex matrices completely behind. We're entering a space that just has basic addition and multiplication, but literally no guaranteed numbers or traces. The security here is much, much tighter.
Now, before we tackle a completely naked, arbitrary ring, let's look at a matrix ring over an arbitrary base ring, which we'll call S. Infiltrating this kind of general space requires setting up very specific shifting matrices, P and D. But the vault only pops open if the base elements, these things called central units, which basically play nicely with everything else, perfectly sum up to the number 1. If and only if that condition is met, then the commutator raised to the power of n perfectly equals the identity.
All right, here is the absolute ultimate abstract target. What if we just have a completely arbitrary ring R, and we somehow find two elements inside it, let's call them little a and little b, that actually satisfy our finite power commutator equation? So the commutator of a and b raised to the power of n equals 1. If this equation genuinely holds true, a massive fundamental structural shift occurs inside the ring itself.
So how do we bypass this security grid? We got to do it step by step. By assuming that the equation ABN equals 1 actually holds true in our ring, the math itself naturally starts spitting out these specific sub-elements, which we'll just call our x and y components. By really carefully multiplying these x and y components together in a very specific sequence, we can literally construct a series of what are known as idempotents. Mathematically, these are elements that don't change at all when squared, like 0 or 1. Think of them as the unyielding physical ridges and grooves of our master keys.
But these aren't just, any ordinary keys. They have to pass some crazy, strict conditions. First off, they must be perfectly orthogonal. That means if you multiply any two different keys together, you get 0, absolutely no overlap. Second, they have to be cyclically equivalent, seamlessly shifting right into one another. And here's the kicker. When you add all these independent keys together, they must perfectly reconstruct the absolute identity, the ultimate oneer of the entire ring.
And when those master keys finally lock into place and meet every single one of those exact conditions, the ultimate payoff is revealed. The arbitrary ring R literally rips off its abstract disguise. The math forces it to reveal its true form. The ring R is actually isomorphic to, which is just a fancy way of saying structurally identical to, a full matrix ring. Just the mere existence of that one single commutator equation forced the entire abstract space to organize itself into a grid of matrices. We didn't just steal the identity, we forced the universe to show us its hidden blueprint.
So I'll leave you with this. If cracking just a single commutator equation can force a completely formless mathematical space to reveal a highly organized matrix architecture, what other hidden structures are out there in the vast, unexplored plains of algebra, just waiting for the right logical master key and the perfect mathematical heist? Thanks so much for joining me on this explainer, and keep questioning the hidden structures around you.